first order chemical reaction. What is half-life period? That is time required to reduce half of the initial concentration of the reactant of a first order reaction is called half-life period of a reaction. Now from the kinetics, first order kinetics, from first order chemical reaction, from first order chemical reaction or first order reaction, K is equal to 2.303 divided by T log base 10 of R naught divided by R. R naught divided by R. Where K is equal to velocity constant of the first order reaction, T is equal to half-life, that is time required to bring about the chemical change. R naught is initial concentration of the reactant and R is the concentration of the reactant at an instant of time t, where K is equal to velocity constant of first order reaction where K is equal to velocity constant of first order reaction, R naught is equal to initial concentration of the reactant that is in moles per liter, moles per cubic decimeter or moles per liter. R is equal to concentration of the reactant at an instant of time t, that is also in moles per liter, whereas T is equal to time required to bring about the change, This is about the explanation of the variable factors in the K representation of the first order reaction, that is velocity constant of the first order reaction. Now during half-life period or at half-life time, R is equal to R naught by 2. Then T is equal to T half. That is equal to T 0.5. T half, on some textbook it is represented as a T 0.5. What is by half-life period of first order reaction? The time required to reduce the half of the initial concentration of the reactant in a first order reaction is called half-life period of the first order chemical reaction. We know that from velocity constant of the first order chemical reaction, this is a representation. Yesterday we solved problems based upon this. K is equal to 2.303 divided by T log base 10 of R naught divided by R. Expand all the variable factors. K is equal to velocity constant of the first order reaction. R naught is initial concentration of the reactant in moles per liter or moles per cubic decimeter. R is equal to concentration of the reactant at an instant of time t in moles per cubic decimeter. T is equal to time required to bring about the change, and during half-life period or at half-life period, R, that concentration at an instant of time t, is given by R naught divided by 2. Then T is equal to T half or T 0.5. Now this, consider this is in equation number 1. Consider this is in equation number 1. Now substitute the values of this T and R in this equation number 1. Then what about the expression? What about the expression? What about the expression? Substitute the values. Substitute the values. Substitute the values. At half-life period, T is equal to T 0.5. R is equal to R naught divided by 2. R is equal to R naught divided by 2. R is equal to R naught divided by 2. Substitute the values in this equation. Substitute these values in equation 1. Then K is equal to 2.303 divided by T 0.5 log base 10 of R naught divided by R naught divided by 2. R naught divided by 2. This is equal to K is equal to 2.303 divided by T half into log base 10 of 2 R naught divided by R naught. This rearranging 2 R naught and R naught will get cancelled. Therefore, K is equal to 2.303 divided by T half into log 2. We know that log 2 is equal to, we know that, but log 2 is equal to 0.3010. And hence K is equal to 2.303 divided by T half into 0.3010. Therefore, K is equal to 0.693. Multiply this is equal to T 0.5. Consider this is therefore T half is equal to or T 0.5 is equal to 0.693 divided by K. This is the very important formula used to determine the half-life period of the first order reaction, whereas the K is the half-life period of the first order reaction. Therefore, whenever the half-life period is given, then velocity constant of the first order reaction can be calculated, or when velocity constant of the first order reaction is given, half-life period of the chemical reaction can be calculated. Now this is when K calculation by T half known, T half calculation when K is known, Now this is about the derivation of the half-life period of the first order chemical reaction. Now see the expression, T half is equal to 0.693 divided by K. I will rewritten as this is T half is equal to 0.693 divided by K into 1 divided by K into 1. You know that 1 can be rewritten as R naught to the power of 0. R naught to the power of 0. Therefore, T half is equal to 0.693 divided by K into, this is R naught, initial concentration, to the power 0. Now, this is 0th power of the initial concentration of the reactant. Or it does not come the initial. It does not contains any concentration terms like R and R naught, and hence half-life period of the first order reaction is independent of the initial concentration of the reactant. Independent of the initial concentration of the reactant. Is it clear? This is very important one. Independent of the initial concentration of the reactant. In some cases, they will ask derive an expression for half-life period of the first order reaction, or how do you say that the half-life period of the first order reaction is independent of the initial concentration of the reactant. Or you can rewrite there is a T to the power of T first order, or T first order, or this is a T first order. If it's because if so many reactions are there, a second order reaction, then the confusion. That is why just for our safer side I mentioned it is the first. T half means half-life period of the first order reaction. Half-life period of the first order reaction. Half-life period of the first order reaction, or half-life period of the first order reaction. This is half-life period of the first order chemical reaction. Half-life period of the first order reaction is independent of the initial concentration of the reactant. Independent of the initial concentration of the reactant. Now see, this is for an expression. Half-life period of the first order reaction is equal to 0.693 divided by K into 1. K into 1 K into 1 or T first 0.5 is equal to 0.693 divided by K into initial concentration to the power 0. Initial concentration to the power 0. If initial concentration is R0, then R0 to the power 0. R0 to the power 0. See, if it is a first order reaction, then it is a 0. If it is a second order chemical reaction, then it is equal to, consider this is, therefore this half-life period of the first order reaction is inversely proportional to the 0th power of the initial concentration of the reactant. 0th power of the initial concentration of the reactant. Now this is very important. Show that the half-life period of the first order reaction is inversely proportional to the initial concentration of the reactant. Inversely proportional to the initial concentration of the reactant. If I represent this initial concentration as a, that is R0, that is equal to R0. This is initial concentration to the power 0. Initial concentration to the power 0. If it is a first order reaction, if it is a second order chemical reaction, then both are changes. If this is second order chemical reaction, that is inversely proportional to the initial concentration of the reactant. If it is a second order reaction, then T half of the second order reaction is inversely proportional to the first power of the initial concentration of the reactant. If it is a 1, it is 2, it is 0, it is 1. If it is a nth order reaction, then it is inversely proportional to the n minus 1th power of the initial concentration of the reactant. For a third order reaction, it is inversely proportional to square of the initial concentration of the reactant. Half-life period of the third order chemical reaction is inversely proportional to the square of the initial concentration of the reactant. If initial concentration is represented by means of the R0, then R0 to the power of 2 or R0 to the power of 1. Now T half is inversely proportional to zeroth power of the initial concentration of the reactant. Half-life period of the second order reaction is inversely proportional to the first power of the initial concentration of the reactant, and half-life period of the third order chemical reaction is inversely proportional to inversely proportional to square of the initial concentration of the reactant. Square of the initial concentration of the reactant. Is it clear? Therefore, for nth order chemical reaction, this is inversely proportional to n minus 1th power of the initial concentration of the reactant. Initial concentration of the reactant. Okay. Now, what is half-life period? Assume that is a initial concentration. Assume that is initial concentration. If it is 100 moles, after first half-life period, after first half-life, after first half-life, then it is reduced to 50 moles. 50 moles. Then in second half-life, this is 25 moles. 25 moles. In third half-life, 12.5 moles. In fourth half-life, this is 6.25 moles. 6.25 moles. In fifth half-life, it is 3.125 moles. 3.125 moles. Then sixth half-life, this half 3.125 divided by half. 3.125 divided by half. Three 1.25 divided by 2, 1.5625. 1.5625. Seventh half-life, this divided by 2, that is 0.78125 moles. This is in terms of moles. Eighth half-life. Again, this is half. 0.3906 moles. Ninth half-life. After ninth half-life, this divided by 2, 0.195, 3 moles. In 10th half-life, this divided by 2, 0.0976 moles. 0.0976 moles. Okay. Now, suppose initial concentration is 100 moles. In your entrance exam, they will ask the problems based upon this. In second half, after first half-life, 50 moles react and 50 moles that is present. 50 moles react and 50 moles present. 50 moles present, 50 moles left, 25 moles, there is a 50 moles, 50 plus 25, similarly you can calculate, there is a 25 moles, 50 plus 25, 75, 75, 25 that left, 50 plus 25 plus 12.5, that much 87.5 that would react and 12.5 that left. Please take this chart, this is very important chart. Then in order to calculate how many half-lives will be completed to reduce this much concentration of the reactant, they will ask in entrance exam point of view. In entrance exam point of view, this is very important one. T 50% is equal to 1 into T half. If in a problem they mentioned 50% completion of the chemical reaction, T 75%, time required to complete 75% of the concentration of the reactant means 2 half-life periods will be complete. There is a T 87.5%, that is 3 times of the half-life period are complete. Then T 93.75%, 4 half-life periods are complete. If T 96.25% completion, this implies 5 half-life periods, 5 half-life periods, and so on. Sir, how we will get these values? How these values? See, initial 100 moles, 50% completion is 50 moles, remaining is 50 moles. Then again 25 moles completion. Then this is first half-life, 50% means first half-life. Then half of this value, that is equal to 75%. Then half of this value is 25 moles. 25 moles. This is first half-life. That is T half number 1. T half number 1. That is 1 into T half. 1 into T half. Now this is a 2 half-life. 50 plus 25, that is equal to 2 half-life periods. 2 half-life periods. Now again 12.5 moles. See, this is 87.5. That is a 3 into half-life period. 3 into half-life period. 87.5 completion. 75% completion. 75% completion. 87.5% completion. 87.5% completion. Again half of this value, 6.25 moles that left. Now all this connection, that is the fourth half-life period. Fourth half-life period. 87.5 plus 6.25, 93.75 completion. 93.75 completion. Again 3.125 moles, 5 half-life, 5 into T half. Then 93.75 plus 3.125, that is equal to 96.75. something. 96.25, 93, 87, 93.75, 3.125, 5, 7, 8, 6, 9, 96.875, 96.875, 5 half-life, 96.875% completion, 96.875% completion. Like this we can derive the formulas of the half-life period of the first order chemical reaction. Half-life period of the first order chemical reaction. Okay. See, it is a first order reaction problem. First order reaction problem in half-life period of the chemical reaction problem. Half-life period. Here the rate constant value is given. We know that half-life period of the first order reaction half-life period of the first order reaction we know that half-life period of the first order reaction T half is equal to 0.693 divided by K, where K is velocity constant of the first order reaction, where K is equal to velocity constant of the first order reaction. First order reaction. That is given in the problem, that is equal to 5.36 into 10 to the power of minus 4 per second. Substitute the values in this expression. So T half is equal to 0.693 divided by 5.36 into 10 to the power of minus 4. When 10 to the power of minus 4 comes to the numerator, then it becomes 10 to the power of plus 4. 0.693 into 10 to the power of 4 divided by 5.36. That is in terms of seconds. 1930 divided by 5.36 seconds. That is equal to divided by 5.36. That is 1292 approximately seconds divided by 60, that is in terms of minute. That is equal to divided by 60, that is 21.54 minutes. 21.54 minutes. Okay, these are very simple problems. Usually they will ask in board exam for 2 marks questions. In a chemical kinetics, 1 mark questions will be there, 2 marks questions will be there, and 5 marks questions will be there. In this 5 mark questions, then 3 plus 2. Usually they will ask in 2 marks this type of half-life period of the chemical reaction problems. Okay. Thank you, students. This completes about the half-life period of the first order chemical reaction. I will continue the remaining topics in tomorrow's class. Thank you.